Alright, we haven't always known about atoms, okay? 2,000 years ago, people were debating what matter was made out of, but it wasn't really until the late 1700s that we actually had a modern model, or a scientific model of the atom. There was an English scientist by the name of John Dalton, and he was studying matter. He was looking at how it's put together, what it's made out of. He did a whole bunch of different experiments, burned some metals, saw the reactions that occurred, and he came up with some rules about matter. Okay, and he came up with a model of the atom. So this is John Dalton's atomic model. Okay, and he was really the one who started the modern version of the atom. Okay, and so what John Dalton said is, he said, all matter is made of atoms. Okay, and atom really means uncuttable. So these are the smallest little parts. Okay, all matter is made of atoms, and atoms are indivisible. It's as small as we can get. There is nothing smaller than an atom, according to John Dalton's model. Okay? Atoms are the smallest as we can get, and all matter is made of atoms. Okay? Another main point from Dalton's theory is that atoms of a given element, so like if we pick one, say lead, atoms of a given element are identical. Okay, so every single lead atom is just exactly like every other single lead atom. Okay? And this is Dalton's model of the atom. And there's a few other points that he had and people could test. These are the main ones for us. All matter is made of atoms, atoms are indivisible, and atoms of a given element are identical. So if we were going to model, if we were going to draw a picture of Dalton's model of the atom, what he thought is that atoms were just basically little tiny blocks, and so we have this kind of spherical shape or whatever, and all atoms of the same element were identical and atoms of different elements were different. He thought maybe their shapes would vary slightly, or they had different little pieces on them to help them form bonds, but essentially John Dalton says atoms are as small as we can go, everything's made out of atoms, but atoms are indivisible. Okay? Which is all well and good, but when people propose things like this, other scientists take a look at that and they're like, well, let's see if you're right. Okay, and so later there was another scientist, his name was J.J. Thomson, okay, and he did an experiment with a cathode ray tube, and there's a really cool video about it, and you can find it on YouTube. But essentially what J.J. Thomson did was he had a little vacuum chamber, only it wasn't quite a vacuum chamber. Inside a tube he had a few particles of air, okay, and he applied an electric current to it. So he had positive going to one side, he had negative going to the other side, and he hooked this whole thing up to a battery. Okay, actually he used a pretty big voltage source, but okay, powers this thing up, and when he did that, this beam shot from one side to the other. That's called a cathode ray. Okay, now that's not a big deal of itself, but what he was able to do was bring positive charge up next to this thing, and when he did that, when he brought a positively charged plate up next to it, this blue beam bent down towards it. Okay? When he put a negative charge up next to it, the beam bent away from it. Okay? And the video, I'll post a link to it, shows that, and it's pretty cool. Okay? But all of a sudden this means atoms contain charge. Okay? So, because this beam, the reason it's being repelled or attracted by these different forces is because this beam is charged. And since the only thing in this little tube was a few particles of air, a few air atoms, he was able to say that atoms contain charge. Okay? And not only that, these particles that have the charge can be separated because this beam has a negative charge. Okay? Which means there must be a positive part too, because atoms are neutral. Okay? So Thompson, and this is called the cathode ray tube experiment, okay, because this tube that he has is a cathode ray tube. Thomson was able to actually alter Dalton's model a little bit. Okay, so his model is called the plum pudding model. Okay? And plum pudding is an English dessert, and I'm not really sure what it is. Okay, I call this the chocolate chip plum dessert. Really, I just wrote that. Okay, I'm not really sure what it is. I've never had plum pudding. Okay, it doesn't sound appetizing to me at all, but I'm guessing it's some kind of dessert that has little chunks of plum in it. I call this the chocolate chip cooking model of the atom, because no longer is a solid little sphere going to work. And so what Dalton said was, okay, there is still a big chunk of atom, and it has a positive charge, but stuck to that big chunk are little pieces of negative charge. Okay? And we can get these things to separate, and so atoms are no longer the smallest thing. Okay? atoms contain smaller things called electrons. And so Thomson is credited with discovering the negatively charged particle in the atom, and he called it the electron. Okay, so Thomson discovered electrons, and electrons are the negative particles in an atom. Okay, but that's where Thomson left it. Okay, he's like, okay, so atoms are no longer indivisible; they have a plus and a minus charge, but they're still, everything else is true. Atoms of the same element are the same. Atoms of different elements are different. But this is where we're at. Okay, well, this worked for a while, but then another guy came along, right? This guy's name was Ernst Rutherford. Okay, and so Rutherford had his own little model of the atom. Okay, what he'd actually discovered were these things called alpha particles, and alpha particles are basically the bullets of the atomic world. Okay, and so he found these positively charged particles that move really, really fast and have the ability to move through things, right? And so he was just seeing how they reacted to different things. And so what he did was he took a gold sheet, a really, really thin piece of gold foil, okay, and he took these alpha particles and he put some film around this so that he could see if any alpha particles hit it. Okay, but he took an alpha particle source and he started shooting alpha particles this way. Okay, and since these little alpha particles are really small, move really fast, he expected them to just blow right through this gold, and he expected to see a whole bunch of stuff line up over here. Okay, which mostly happened, but occasionally some things got deflected a little bit, which, alright, that's okay, it happens. But then some of them bounced straight back, or almost straight back. Okay, now this is just like shooting a bullet. If a bullet's going to bounce off of something and come back, that means it hit something that was fairly big, fairly massive. Rutherford didn't expect this at all, and he tried to figure out, okay, what's actually going on in there. And so if we could, his proposal was that if we could zoom in and look, we would find that the atom is mostly empty space. Okay, and so he's saying, okay, here's an atom, here's an atom, here's an atom. Okay, and my gold foil is made up of a whole bunch of these little atoms, and they're kind of stuck together because it's a big chunk of gold, but most of this atom is empty space. In the middle, there's a big dense spot. Okay, big dense spot, and that's why when I send these alpha particles through, most of them go through, or if they don't go through, they get deflected just a little bit. Okay, but occasionally an alpha particle hits this big dense spot, and when it does that, it bounces back. Okay, and so this model of the atom didn't have everything distributed equally. It had all the mass concentrated in the center of the atom, and most of the actual volume of the atom is empty. There's little electrons buzzing around it. Okay, and so Rutherford, what he really did was discovered the nucleus. Okay, Rutherford discovered the nucleus, and his experiment is famous. Okay, it's called the gold foil experiment, and it basically changed the atom one more time. So if we had a progression, a final timeline of the atom, of everything that happened, okay, what we did is we started with Dalton, who said, okay, everything's made out of atoms, but atoms are as small as we can go. Okay, so we had this big chunk, and that was it. Okay, then we moved on to Thomson's model of the atom, and Thomson said, yeah, we've got atoms, but they're not as small as we can get. We can have charges on them. We know there's charges within the atom, so they can't be as small as things get. Okay? And Rutherford took it one step further. He's like, okay, I agree, there's charges in the atom, but it's not distributed all over the place like Thomson showed. Instead, most of the positive charge, or all of the positive charge, is concentrated in the very center of the atom, and around the atom are where the electrons move. Okay? And so he had this kind of model, and that was Rutherford's model of the atom. Okay? So through different experiments and by testing these theories, we were able to come up with a fairly accurate representation of the atom, and this was, from the late 1700s through the early 1900s when they were actually doing these experiments and coming up with the model of the atom.